All right, on page 650, we're going to talk about the ionization product of water today. So you can turn to page 650 in your Glencoe Chemistry, Matter, and Change textbook if you wish, and follow along here. So one of the terms that we've talked about in previous lessons here is, make it official here today, but water is said to be amphoteric because it can act both like an acid and a base. So we've talked about this characteristic of water before. It's very important. In the presence of a strong acid, it will act as a base and absorb that proton that the acid gives off. In the presence of a strong base, it will donate its proton, therefore producing those OH minus ions in solution. So water, very special, can act both like an acid and a base. Think about the root word to amphoteric, amphibious, amphibian, water, land, right? An amphibious vehicle can float on the water and can also drive on the land or whatever. It's amphibious. So there's a dual sort of nature to it. Because water dissociates slightly, right? Dissociates. If you're following along with your blank notes here, you can put dissociates there. It dissociates slightly and predictably into H plus ions, and actually they're H3O plus ions, the hydronium ions. The textbook usually just writes H plus. You'll see that often, but we know that the protons don't really float around in solution all by themselves. It's hydronium ions and hydroxide ions. So we know that we have H2O, okay, and that actually dissociates, it gets into equilibrium with a small amount of, and if we want to write like this, H plus OH minus. Okay, so it auto dissociates automatically, predictably, but very slightly, very slightly. And this value right here is a very small number, and this is called the Kw. Okay, it's a special solubility product constant, and we give it a symbol Kw, just like KEQ, KSP, Ka, Kb. It's a solubility product constant special for water, such that the product of its ions that's H plus and OH minus. And if you like to, let's do this. So H3O plus OH minus. There you go. So if you like the hydronium ion, which we've been learning a lot about, there you go. Okay, so that's the balanced equation there. So it breaks up predictably into hydrogen ions and hydroxide ions. And just like KSP, the product of the ions to the powers of whatever the coefficients would be in the balanced equilibrium equation there. So in this case, exponent 1 on these two. If you multiply the product of their concentrations together for water, the Kw is 1 times 10 to the negative 14. So the product of these will always equal this. Always, always. Okay? Now, when acids or bases are introduced into solution, there will obviously be a little bit more of the hydronium ion or the hydroxide ion. But as one goes up, the other must go down because the product always has to be the same. And so that's going to be very helpful for us to determine pH, pOH, and the measure of acidity and basicity of different solutions. This is going to be very, very important for us. So this value holds true even when acids and bases are added to water. We can use this expression to calculate concentrations of hydronium and hydroxide ion. So if you're filling your notes in there, you got some blanks. I'm not sure why those are on separate lines. So concentrations of both the hydronium and the hydroxide ions. As well as this is very useful for calculating pH. And we haven't talked a lot about pH here yet, but we're going to get to that here shortly. So this first part is this Kw, just introducing Kw, and it is the product of the concentrations of the ions that make up water. It's a very special constant for water. Okay, so the question is, what are the concentrations? So we're given the Kw, but what are the concentrations of these ions in solution? It's obviously going to be pretty small. How small? How do we figure that out? Well, Kw is 1.0 times 10 to the negative 14. Just like KSP, that has to come from the product of the ions that make up the water. So here we'll use H plus or H3O plus, doesn't matter, same thing. Each to the power of 1 because they break up, just like this equation up here, they break up at a 1-to-1 ratio, right? Okay, so this is what we have, just like a special KSP. And because it's a 1-to-1 ratio, if I wanted to solve for the concentrations here, I could just let each of them be x. So watch what we get. X times x, or x squared. Just like we did KSP, very, very similar. And so now if I take the square root of both sides, the square root, and you can do that in your calculator. I'll do that on my calculator here. It's actually pretty simple, but let me just show you. It's not real difficult to do. So 1.0, and you're going to want to use your scientific notation exponent times 10 to the power of button. In this case, it's my EE button. I'm going to do negative 14. And whoops, I got to take the square root of that. So let me just hit equals so I can reset the square root of my answer there. In this calculator, you got to put the square root first. And so that the square root of this is 1 times 10 to the negative 7. And that makes sense. If you have an exponent on a variable, let's say, you always half the exponent if you're taking the square root. So if this is 1 times 10 to the power of negative 14, it's 1 times 10 to the negative 7. That's what x is. So therefore, the concentrations of H3O plus, or H plus in your textbook you'll see, and OH minus are both the same, and that concentration is 1.0 times 10 to the negative 7, and this is always going to be in moles per liter here. Yeah, remember our units? It's always in moles per liter. So in a sample of pure water, it's going to be mostly water molecules, obviously. But the concentration of the ions, because of this auto-predictable, very weak dissociation, we are going to have a predictable concentration of each of those ions. All right? So that's the base point. Now, if we have any more of any one of these ions, that solution is now going to be either a little bit acidic or a little bit basic. And that's the case here with this next question. So if the OH changes, now let's say we add sodium hydroxide or some other strong base, and we've added some new hydroxide ions, and the concentration is now 2.5 times 10 to the negative 9. How does that change the concentration of the hydronium ions? Well, this always holds true right here. This always holds true. So if we have a new value for this, I just solve for this one now. Okay? No problem. Pretty easy. So 1.0 times 10 to the negative 14 is always the kW. That always is where you start. And I don't know the concentration of H plus or H3O plus, but I do know this concentration. It's 2.5 times 10 to the negative 9. Notice that I use square brackets when I'm talking about concentration. I'm using round brackets when I'm actually given a value. Okay, you don't have to use square brackets here, just use round brackets for the number. I'm going to divide both sides by this number. See that? And that's going to give me the concentration of H3O plus. H3O plus is going to be, let's do that on the calculator. So I have 1 times 10 to the power of negative 14 divided by 2.5 times 10 to the power of negative 9. 4 times 10 to the power of negative 6. 4.0 times 10 to the power of negative 6. Do sig figs there, 2 sig figs, so we'll write 2 sig figs there. And yeah, so that's going to be in moles per liter. And so as you can tell, you see this here, negative 9. That's actually a little bit less than negative 7, right? 10 to the negative 7. So this goes down. That means that this has to go up slightly. And 10 to the negative 6 is greater than 10 to the negative 7. So now we have a slightly acidic solution here. Okay, because we have more hydronium ions than this concentration. You see, when these are equal and they're equal to this, that means it's completely neutral. So if the concentration of H3O plus goes up, then we have an acidic solution. And that leads us to the pH scale, which we're going to study here next. So let's talk about the pH scale in this lesson. If you're in your Glencoe Chemistry, Matter and Change, you can turn to page 652 and 53. 652 and 653, that's where we're going to talk about the pH scale. So the pH, when we talk about pH of solutions, we're talking about the acidity of these solutions. So how acidic is it? And this is a picture of the pH scale, and I like this because we have numbers associated with pH. So pH of 0 is extremely acidic, almost as acidic as you could possibly be. And we're talking like battery acid, pH 1 is stomach acid, 2 is lemons, soda pop, tomatoes, you start to work your way up. Now, milk is slightly acidic, That's probably a shocker to some of you. And blood is slightly basic. Oh, I don't know if you guys knew that. They're pretty close to exactly neutral, but milk is actually just slightly acidic. We usually, drink milk to calm our stomachs down. If we have something or spicy food, milk or sour cream or some dairy products, we think, oh, that's kind of a opposite effect to these kind of rank, spicy. We think of spicy as acidic. Tomatoes a bit acidic. Milk is pretty close to neutral, but it isn't basic actually. Now, water would be our perfect example of perfect neutral if we're just talking about H2O molecules, right? Because it has an exactly equal number of hydronium ions and hydroxide ions, so they're exactly equal. That makes it neutral. So there are some things, of course, on the upper end of the pH scale. This is very alkaline or basic. So acidic, the other word for alkaline is basic. You may be not familiar with alkaline, but extremely basic here. So these household cleaners, bleaches, drain cleaners, they eat away at different things that are clogged in the drain, but not an acidic sort of eat away. It's a very, very basic, strong base. Okay, so that's just a visual measure of the pH scale. Now these colors are interesting too. If you have like test paper, like pH paper, you might see that very acidic is red and neutral is close to green. Very basic would be violet or blue or indigo, violet, blue sort of thing. And so those colors on that kind of pH paper means something too. Okay, so what is pH? Mathematically, we can look at what pH is here. So here's the formula for finding pH. I'll just make that a bit bigger. Okay, so the P kind of represents this negative logarithm. Now, if you haven't been in too many math classes, if you're not a math person, you maybe don't remember about logarithms. Logarithm is a function. It's on your calculator. And what logarithms are, basically logarithms deal with exponents. And for this logarithm, we have a base 10. So the logarithm of something basically is saying, well, what's the exponent that you put on 10 to get this number? Okay? So logarithms are related to exponents. And we'll go more into this a little bit later. But the P is log. Now the H, obviously, is the H+, or the hydronium ion concentration. So pH is negative logarithm of the hydronium ion concentration. So if you have the concentration, you simply plug it in and you can find the pH value. So let's go back to this last example. And here we had a hydronium ion concentration of 4 times 10 to the negative 6 molar. Okay? So let's find the pH, and we simply just use our math here. The pH, it's a small p and a capital H. Yes, it is a bit strange, but that's the way it's written. So what we do is we type in the negative logarithm of 4, what was it, 0.6? 4.0? 4.0 times 10 to the negative, ooh, come on now. 4.0 times 10 to the negative 6. You don't have to put your units in there, you don't have to. But this is, your calculator is going to be able to take care of this, all right? So you turn your calculator on, and I'll show you where the logarithm is. It's right here on my calculator. You'll have a LOG button probably. Very clear on yours. So we'll do negative log of, and you just pump in this number. Now, if you don't like scientific notation and you want to just write the decimals, you can. That'd be 0 decimal. Now, with 10 to the negative 6, so this decimal moves back 6 places. So that's going to give us 1, 2, 3, 4, 5 zeros, and then a 4. You see that? That's the same number in regular standard notation. So you can just type it in that way too if you don't like the scientific notation. So this answer, now 5.3979, let's go with 2 sig figs, so 5.4. So the pH here in this example is 5.4. 5.4. So we're talking right about here, approximately the same acidity as something between coffee and milk. Slightly acidic, just slightly acidic. Okay, but that's how you find the pH is using logarithms. Now, before I get to pOH here, actually, I just want to include something here. When we're talking about logs, here's the thing: the pH of neutral water. Okay, watch this. If we have neutral water, it's 1.0 times 10 to the negative 7, just a pure sample of water. The pH is exactly 7. Here's another example. What's the pH of a solution that has this for a hydrogen ion concentration? 1.0 times 10 to the negative 3. Well, without even going onto my calculator, I know that that's 3. Okay? So here's a shortcut. You ready for this? Watch this. All right. If you have a 1 here, it's almost like 1 times. That's gone, right? Okay. So what's the log of 10 to the negative 7? Well, remember, logarithms have a base of 10. So it's kind of asking you, what power do I raise 10 to get 10 to the negative 7? Oh, and then by the way, we're going to multiply that answer by a negative. So what you do is if there's a 1 here, like there was before, all you have to do is change the sign here, and that's your pH right here. You see? So it's a 1 here. So guess what? My pH is 3. It's as easy as that. Now, obviously, if this moves from 1 to another number, it's not going to be exactly 3. It's not going to be exactly 3, but it's going to be pretty close. This is just a little bit more than 1 times 10 to the negative 3. So guess what? This pH is going to be just a little bit less than 3. I don't know if it's 2 to the... Well, let's find out. That's my guess. See how close I was. Okay, but just let that sink in for a bit, because there is a bit of a shortcut with pH, and is a good way to approximate. Even when you see this number, the pH is going to be pretty close to that exponent. The positive version of this number right up here is an exponent. So let's do this. Negative log of 2 times 10 to the power of negative 3 gives us 2.7. Oh, it's pretty close. 2.69, 2.7, okay? 2.7, but you see what I'm saying, right? Okay, so that's a little bit of a shortcut. That's how pH works. Now, there is such a thing. There is such a thing as pOH. pOH. pOH is the negative log of the, yeah, that's right, hydroxide concentration, OH. Now, we usually deal with pH. We don't really talk in terms of pOH very often at all, but the pOH and the pH are related, okay? Just like the hydrogen ion concentration and the hydroxide ion concentration are related, pH and pOH are related. And if you find the pH, you can easily determine the pOH, because the sum of the two have to equal 14. And the reason why that is 14, you probably are maybe thinking back to, well, where did we just learn about a 14, right? Back up here, look at this. You see how this product always has to equal 10 to the negative 14. Okay? So 7 and 7, or 6 and 8, or 5 and 9, so on. So pOH and pH are related there. The sum has to always equal 14. Okay, so here's example problem 2 from your textbook here. And it's basically says, hey, calculate pH from a given hydrogen ion concentration, no problem. Okay? Neutral solution. Okay? So there's nothing extra in there. Nothing extra to bump the pH. We're just going to worry about the H plus concentration. Just pure sample water. It's equal. It's neutral. And so this is what we did. We just found out, hey, the H plus, if it's a neutral straight water solution, H plus concentration has to be 1 times 10 to the negative 7. And that pH, when you plug that concentration into the negative logarithm function, you get 7, or 7.00. Okay? Pretty straightforward there. Now, here's some questions from the text. 24 to 31, these all deal with pH, and I am going to give you a chance now to work on these questions. These are very similar to what we've done. Okay, number 26 is a bit of a challenge because it asks for pH and it gives you the OH. All right, so remember, you have to determine either the pOH to find the pH, or you have to determine the hydrogen ion concentration given this to determine the pH, one of those two methods. So you go ahead and give these questions a try. Also, you can do 27, 28, 29, and I believe there's a, oh yeah, I'll give you some hints on 30 and 31 in a bit. But anyways, here, to get you started, here are some of the solutions for 27. These are pretty straightforward. There's the solutions for 27. And you can pause the video now, work on 27 through 29, and I'll show you the answers in just a few minutes. Okay, so here's the here the solution is to 24. We're going back to 24. pH, just the negative log of the hydrogen ion concentration that we are given in the question. So here it's pH 2. Remember our little shortcut. If this is a 1, pH is exactly 2. So plug in hydrogen ion concentration into your calculator. For this one, you should get a pH of 5.52. So for 24, these are your two answers. For 25, okay, the answer for A, calculate the pH. So again, you just plug this value into your log function and you get pH, should get pH of 2.26. And again, for B, 4.08. Okay, 26, I would like to show you, this is a bit, I don't know, this is kind of a little bit goofy here. It seems like this is a bit confusing, this here. So, and there's two ways you could do it. There was a typo. There's two ways you could do it. Like I said, you could first of all find out what the hydrogen ion concentration is, and you take the Kw right here, and you divide it by the OH concentration that you're given, and that gives you a hydrogen ion concentration of 1.2 times 10 to the negative 9. You put that into your negative log, and you should get your pH. That's option 1 for 26. The other option is to find the pOH first. So go ahead and plug your OH minus concentration into this log equation, and you get your pOH. From there, you remember that pOH and pH have to add up to 14. So let's take 14, we'll subtract the pOH, that should give us the pH, and you get virtually the same answer there, okay? 8.92, 8.91. So that's 26. And here are your answers for 27. Calculate the pH and pOH. Oops. Should highlight the pOH here too. 27A. And B. There's the answers for C and for D. Okay, 28. And again, very similar, pH, pOH right there. And B. 29, we'll pause at 29 here. I'll show you 29, then I'm going to show you how to do 30 and 31. It's just slight, something you got to add here, slight difference in calculating for 30 and 31. Okay, so let's head back to our notes here. Okay. So this last type of problem you have to do for this lesson here, last type of thing you have to know how to do is how to calculate the concentrations from a given pH. Okay, concentrations from a given pH. So if we're given a pH of, in this question, it's 7.4, I need to know what the concentrations of hydronium and hydroxide ion are. All right, so what do you want to notice on your calculator? Okay, finding pH, we use the log function, right? The log function, that's what we did here. But finding the concentration given the pH will require the inverse function. And if you look at your log button, the second function of the inverse function of log is, that says 10 to the power of x. Okay, 10 to the power of x. So this is what we are looking at here. So for this one, we know that pH equals the negative log of the concentration of H+. If we're given the pH here, how do I find H+? Well, it's actually not that hard. I'll show you what you do. First of all, you get rid of this negative sign, okay? So you're going to want to divide both sides by a -1. That puts the negative over on the other side. That's the first step. Now what we do, in order to get rid of the action of taking the logarithm of something, in order to get rid of this, what we do is the opposite operation, which the second function on your calculator raises this to a power, as an exponent on 10. So literally 10 to the power of -7.40 equals the concentration of H+. Now this might make sense because remember our little shortcut we talked about earlier in the lesson? Remember this? If you're given this with a 1 here, which is basically what we have, then the opposite of this is going to be the pH. You see, if this is the concentration, this is the pH. That makes sense. So again, working backwards, all you have to do is take the concentration, you take the pH, you throw a negative on it, and you raise 10 to that power. That's how you get your concentration. Okay? So here, I mean, you could write it like this if you want. 1 times 10 to the power of negative 7.40. And yeah, so let's go down here. Now, what is that? 10 to the power of negative. You don't want to leave it like this. Probably you want a decimal or something like that. So let's keep going. Let's finalize this. So 10 to the power of, and I'm going to use my second function here. So second function, see, 10 to the power of. I'm going to put it in negative, excuse me, 7.40. And I get 3.981 times 10 to the negative 8. Or 3.4 times 10 to the negative 8. Wait 1 second. Right, I'm not sure why I put 3.4 there. That's 3.98, and to 2 sig figs would be 4.0, so that's why they have 4.0 there. Now, just looking back here, they have 3 sig figs here, so let me see that number again. 3.98. Yeah, you could go 3.98 as an answer. That would probably be appropriate. 3.98. Okay, and that, again, that's molar, right? That's the concentration of hydrogen ion, or H3O plus, hydronium. Now, if you're wanting to know the hydroxide ion concentration, okay, you could do one of two things. Again, you could find the pOH and go 10 to the negative whatever. That's the concentration of OH, or you could, go from the Kw expression here. So Kw, remember, is 1.0 times 10 to the negative 14, and that comes by multiplying the concentrations here. All right, so if you want to do that, oops, I'm probably blocking some of that with my face, aren't I? And so now we have this number, so guess what? This is 10 to the negative 14 divided by this number, 3.98 times 10 to the negative 8, and that should equal our hydroxide ion concentration. And if we do that number, this is slightly different than the textbook over here, so you can do it this way as well, right? See, they found the pOH first, and then they did the antilog, or the 10 to the power of this, no problem. But we should get the same answer here. So let's say, oops. No, let's go. Oh, come on now. 10 to hello. There we go. 10 to the power of negative 14, divided by my answer of 3.98 times 10 to the negative 8, should be 2.5, yeah, 2.51. So 2.51 times 10 to the negative 7 molar. That's what you get for your OH minus ion concentration. Got it? Okay. So again, there's actually 2 different ways here that I'm doing. I'm showing you a little different way than this textbook does. They found the pOH first and then did your 10 to the power of, and I found the concentration first and went from there, went from the Kw. So that's how you do it. Let me do the first little bit here for you. For example, milk. Okay, so 30A. Wow, 30A. The pH is 6.50. So what's the, well, this is easy one to find first, right? Because I go now 10 to the negative 6.50. See that? Shortcut, really easy. And let's get a decimal out of there. So second function log, I'm going to put negative 6.5 in there. And that decimal is 3.16 times 10 to the negative 7. 0.16 times 10 to the negative 7. Awesome. Now that is molar. That's the hydrogen ion concentration. Awesome. Okay. Now what about the OH? Oh, that's easy. We'll do Kw divided by H plus, right? That should equal OH minus concentration. So 1 times 10 to the negative 14 divided by my 3.16 times 10 to the negative 7 should equal my hydroxide ion concentration. So what is that? I'm going to do 10 to the power of negative 14 divided by the answer that I have just up there. I'm not going to rewrite it. I'm just going to tell my calculator to use it. Look at that. I get 3.16 times 10 to the 8. It's kind of strange. Same number, different exponent. So there we go. See that? Those should be your answers for 30A. So I will let you now just pause this this lesson, this video, and I want you to do the rest of 30 and 31. Notice, notice here we're given pOH first, not pH like the others. That's the one little challenge part, I guess. So you can find the OH concentration first if you want. All right. There you go. I'll show you the answers in a few minutes. All right, so here you go. Check out your answers to 30. Here's 30A and B. We did 30A, so virtually the same. We went to more decimal places. So B looks like this, and 30C should be over here. So you should be getting for H and OH concentrations, and D. 31, the answers to 31 here look like this right here. So again, you can find the OH concentration first, then use that concentration or the pOH to find your H. Okay, H concentration. There you go. And that wraps up the lesson for today. Yeah, so we talked about, what did we talk about? At the beginning here, we talked about the dissociation of water, so the ionization product constant of water, Kw. It dissociates predictably. We can use this very important number here to find the concentrations of hydronium and hydroxide. We talked about the pH scale, what those numbers mean, how to find pH, and how to find concentrations given pH. And that was our lesson for today. These are questions from your textbook. Encourage you to finish those up. And yeah, make sure you can do all these questions that you need to do. Next lesson will be on neutralization. Acid-base neutralization, titrations, and so on. So yeah.